All right, we're going to do a review of polynomials. This is note card 24. We're starting out here with a function f of x equals 3x to the fourth plus 5x to the third minus 4x squared minus 6x plus 10. This is an example of a polynomial. Poly meaning many. It's just like a plural term. So I have a polynomial with 1, 2, 3, 4, 5 terms. The degree of the polynomial is the highest exponent. So the highest exponent in this polynomial is 4. So this is a fourth degree polynomial, or the degree of the polynomial is 4. The numbers in front of the x's are called the coefficients. So 3 is a coefficient, 5, -4, and -6 are all the coefficients. 5x to the third is one of the terms. I mentioned before that there's 1, 2, 3, 4, 5 terms here, and 5x to the third is one of them. 10 is the constant term. There's no variable, so it's the constant. It never changes. It will always be 10. 3x to the fourth is the leading term of the polynomial. It's the first term, and typically the way you will see polynomials written like this in descending order, meaning that it's written with the terms with the highest power first, then the next, then the next highest, and so forth, and finally your constant. That's the descending order, or also known as standard form. If the polynomial is written in standard form, that means it's written in descending order, highest power, next highest, and so on. The shape of its graph depends on the degree or the highest exponent, and we'll be working a lot with these different graph shapes here. Here we have a parabola or a quadratic, and where it says n equals 2, that means that you will have two solutions. So when you have a quadratic, you have two solutions. When you have a cubic, right here, this is shouldn't be here. That's just a, for some reason, a line on the paper there. When you have a cubic, you have n equals 3 or 3 solutions. Here we have a quartic, kind of the shape of a W, and you have 4 solutions because it would be x to the fourth. And then quintic, x to the fifth, you would have 5 solutions. And that's just a quick review of how polynomials are written and specific things about polynomials. Let's move on to the next note card, 25. Talking about maxima and minima, or in other words, extrema, local and absolute. So I'm going to read through these 4 definitions here, and then we're going to spend some time talking about the differences and the similarities. A local maximum. A local maximum is the highest y value on the open interval. A local maximum occurs at the x value that goes with the highest y value on the open interval. A local minimum is the lowest y value on the open interval. A local minimum occurs at the x value that goes with the lowest y value on the interval. Absolute maximum is the highest y value for the entire domain of the function. An absolute maximum occurs at the x value that goes with the highest y value. Absolute minimum is the lowest y value for the entire domain of the function. An absolute minimum occurs at the x value that goes with the lowest y value. Now that may not make much sense now, but hopefully when I finish talking about this graph, it'll make all the sense in the world. Okay, what we have here, first of all, there are no arrows at the ends here, so on your graph, go ahead and make those little dots there indicating that it stops there. And so what we have here, let's talk about local minimums first. Local minimums. Local meaning in the area of, So in the area of this low point here, this is a local minimum because in this area, this is the lowest spot. So this is a local minimum. Here, in this area of this point is another local minimum because in this area, it is the lowest point. So this is a local minimum. And then finally here, in this area, I had, again, this is the local minimum. In this spot, it's the lowest point. Now, local minimums can also be an absolute minimum. But if I'm talking about absolute minimum, out of these 3 points here, the lowest point of all on the entire domain of this graph is this one. So this is also the absolute minimum. So again, I could have a point on the graph that is both the local and the absolute. Now let's talk about the local maximum. I have a local maximum here because in this area, this is the highest point. And I have one here because in this area, this is the highest point. So this is a local minimum, or I'm sorry, local maximum. And this is a local maximum. And when I'm looking for the absolute maximum, that would be this one here because on the entire domain, this is the absolute highest point. That's the absolute maximum. Now to the right of your graph there, make a new graph. Doesn't have to be perfect. Make you an XY plane. And then make a graph that's similar to this one, but let's make it like this. So if I want to find all of the local minima, then I look at this graph and I see, well, here's a point right here where I have a local minimum because in that area, that is the lowest point. But when I look for the absolute minimum, I can see that this function is going to continue in the negative infinity direction. And whenever it continues in the negative infinity direction, that means that an absolute minimum does not exist because it continues in a negative infinity direction. Now when I'm looking for the local maximum, I can see that in this area, this is the highest point, so this is a local max. But when I'm looking for the absolute max, I can see this arrow indicates that I'm continuing in the positive infinity direction. And so the absolute maximum does not exist. And finally, let's look at note card 26, concavity and inflection points, or points of inflection. What we have here, all of these lines, these are tangent lines, which means basically that they cross this function at a specific point here, but they never will go through the actual curve. What we have here, this curve, this function that we're really looking at, that I want to pay most attention to, is y equals x cubed. And it looks like that. All of these other lines are tangent lines, which means they go through a point on the graph, but they never actually cross through the graph. They just go through a point on the graph. And there's several tangent lines. We'll talk more about tangent lines at another time. But if I'm talking about concavity, we can have concave down or concave up. If it's concave down, that means the graph bends downward. So right here, the graph bends downward. So we have concave down here on this part of the graph because it is bending downward. But it's going to change right here and it's going to start bending upward, which means it's concave up. Okay? And I'm going to talk about a point of inflection in a second. This right here would actually be that point of inflection that we're fixing to talk about because of the fact that it's concave down from here to here, but at this point it starts changing to concave up. And that point of inflection is a point where a curve changes its direction of concavity. And so here on this graph, you can see that reading the graph from left to right, it looks like we are, from here to here, we got concave up, but we have this point of inflection where now it starts to be concave down, or it starts bending downwards. And typically on these points of inflection,